Actually, it is not a presentation. I'm going to do some board works over here. And okay. So if you can see, if you have gone through my video, yesterday's video, you have seen that I have defined two important uh, uh, points, two important terms, one of which is called null space of T, null space of the linear transformation, null space of the linear transformation, which we actually sometimes also call as kernel. And I also defined range of linear transformation, range of the linear transformation, sometimes known as image. Okay, and what are these definitions? According to, if I try to express it in terms of sets, if capital T is the linear transformation, let us name linear transformation by LT, just to save time. Okay, so if T is linear transformation from a vector space V to W, where these two vector spaces, if you can recall, these two vector spaces have been defined over the same field F, over the same field F, then if T is the linear transformation, null space of T is often denoted by NT, or we sometimes call it as kernel of T. Also, you can write it as car-T, kernel of T. It is actually a collection of those points of the vector space V, those points of the vector space V, such that when operated on it, when operated on these points, if we operate the transformation on these points, the image is always the zero vector. And this zero vector, although it is not specifically mentioned in the book, as I can see, this zero vector, remember, is the zero vector of the vector space W. Okay, because Tx is the image, and the image is inside the vector space W. So if I draw the diagram, so this is your vector space V and that is your vector space W. Then if we get a collection of points X such that when applied the transformation on this collection of points, we get only the zero vector over here. So this is actually called, this collection of point is actually called kernel of T, car-T or NT. I hope you have understood. And the second definition which I discussed in the, I didn't discuss this definition in detail, but I mentioned this term. The second definition was of RT, which we call as range of T, or sometimes people write it as range of T also. So this is a collection of points Tx. We choose the points from the vector space W such that there exists a point X belongs to V. There exists a point X belongs to V, so that when Tx is operated on it, we get an image. So if I draw it by a diagram, then if this is your V and this is your W, and if you get a kind of diagram like this, okay, that is called Tx. then this particular set is called range of T. Range of T. So here the transformation is defined by T. It is called range of T, or we will call it as RT. Okay. So this is the thing. These are the two definitions which are most important. Also, the point to be noted, an important point is that we see from the diagram, as I have shown you, that anybody can say that NT is contained in the vector space V and RT is contained in the vector space W. Okay. So question is, can we say that NT a subspace of V and RT as a subspace of W? Can we say it? That theorem, this is a particular theorem which I'm talking about, and it is done on the book, but I'm going to show you how to, because this theorem is also very important and often comes as a problem. So I'm going to prove now in the next page that indeed car T, the null space of T, is the subspace of the vector space V, subspace of the domain, and RT, the range of T, is the subspace of the codomain. Okay, so I'm going to prove it. So my theorem is NT is a subspace of the vector space V and RT is a subspace of the vector space W. NT is a subspace of vector space V and RT is a subspace of the vector space W. So part 1, I'm actually doing this particular problem also keeping in mind that it will be a good practice. Probably you have forgotten how to show a particular subset to be a subspace. So therefore it will be a kind of reminder to you. And I'm treating this particular theorem as a problem. So therefore I am actually first of all trying to solve this particular theorem. Okay. Part 1 is that NT, if I consider this to be part 1 and that to be part 2, so in part 1 I am going to show that NT is a subspace of V. So step 1, it is clear from the definition that NT is a subset of the vector space V. Okay, it is clear from the definition that NT is a subspace of the vector space V. Step number 2, okay, if you have gone through my video of the last class, probably you have seen that I wrote a particular property like this, that if we consider the zero vector of the vector space V, and if I operate the transformation on it, then we get zero vector of W. This was the property, the first property which is stated in the book, just after defining what is linear transformation. So since 0 bar V is the zero vector of V and T of 0 bar V is equal to the zero vector of W. And if you can recall, I'm again writing the definition of NT over here. NT is the collection of all such points of the vector space V such that the image of these points are all zero vector. This was the definition. So carefully observe, It is the collection of all such points whose image is 0. So since the image of 0 vector of vector space V is 0 vector of vector space W, so the 0 vector of the vector space V is actually belonging to NT, NT, and therefore NT is not equals to phi. Step number 2. So NT has elements in it. And step number 3 is that I'm going to use the result, this result, if you can recall, that if x comma y belonging to W and a comma b belonging to F, then W is a subspace. W is a subspace if and only if ax plus by belonging to W. This result was there in the exercise. Probably its number was 20, so far as I can remember. So I'm going to use this result to show that it is a subspace. Let us consider A and B be two scalars from the field capital F on which the vector space V is defined, and we choose and let x comma y be 2 points from the set NT, because we are to show that NT is a subspace. So we have to take points from NT. Since x comma y belonging to NT according to our choice, this implies that T of x is equal to 0 bar W and T of y is equal to 0 bar W. Okay. Now T of ax plus by, what will be its image? That is the point. Since T is a linear transformation, it is given T is a linear transformation, we can apply the linear transformation's original definition over here. And we know the definition is that if a transformation is linear, if T of x plus y equal to Tx plus Ty, and T of Cx is equal to C into Tx. That is the original definition. So I can write it as T into Ax plus T into By. Since Ax belonging to capital V and By also belonging to capital V, as V is the vector space. Okay. And also by scalar multiplication, we can write it as, by this property, we can write this as A into Tx plus B into Ty. A into Tx plus B into Ty. And therefore, you see that according to our choice, this Tx is actually the W bar. So I can write it as A into 0 W bar, means 0 bar of W, not W bar, 0 bar W, 0 vector of V. And B is also being multiplied by the 0 vector of W. And since W is a vector space also, since W is also a vector space, so A into 0 bar W will be equal to 0 bar W, and B into 0 bar W is equal to 0 bar W. Okay, so I can write it as 0 bar W plus 0 bar W, and this is nothing but 0 bar W. So you see that we started from this particular point. And we have shown that the image of this particular point Ax plus By, image of this linear combination, is also the 0 vector of W. And so by definition of NT, this implies that Ax plus By belongs to NT. Ax plus By belongs to NT. So we started with AB belonging to F and XY belonging to NT, and we have come up to this Ax plus By belonging to NT. So from step 1, step 2, and step 3, I'm writing over here. So from step 1, steps 1, 2, and 3, we conclude, we can say that NT is a subspace of the vector space V. So very important result. This result is very important result. Always remember. Okay. As long as you are in touch with linear algebra, you have to remember this result. Okay. Now I'm going to do the part 2 of the problem. So let us do it. I hope that I was going very slowly, and probably we have noted down everything of this particular page. If not, then even if I go to the next page, you have got to know, you have understood the main point, so you can regenerate it. Otherwise, you are going to get it later in the video. Okay. So part 2 of the problem, I am going to show that RT is the subspace of the vector space W. RT is the subspace of the vector space W. Step 1, as usual, I'm going to write it that by definition, it is clear that RT is actually the subset of the vector space W. Step 2, what is RT? Let me write the definition in front of us. Let us keep the definition in front of us, and it is the collection of all such points of W such that for each such point we have some vectors V. So that when the transformation T is applied on this, we get Tx. That is RT. This collection is RT. Since V is the vector space, so 0 bar V is in V, and we know for this 0 bar V, T of 0 bar V is equal to 0 bar W exists. This implies that T of 0 bar V is belonging to RT, and this implies RT is also a non-empty set. RT is also a non-empty set. Okay. Step number 2 is done. Step number 3 is, as usual, I'm going to use this result that if we choose 2 points A, B from F and X, Y from W, then W is a subspace. If and only if AX plus BY belonging to W. Okay. Question number 20, exercise 1.3. So I can write it, I can choose two scalars, A comma B belonging to F, and let us select two vectors X, Y belonging to RT, because I'm choosing the vector from RT because right now I'm interested about RT. Okay. Since X belongs to RT, so there exists a vector small v in V such that T of V is equal to X by definition of RT. And since Y belonging to RT So there exists a vector v prime in V such that T of V prime is equal to Y by definition. So now, as T is a linear transformation, so T of Ax plus By, this can be written as T of Ax plus T of By. This can be written as A into Tx. All these are I'm writing because T is linear transformation. If T is not linear transformation, then I cannot write these two steps. I cannot write these two steps until and unless T is a linear transformation. Now Atx, okay, if I do it in this particular manner, if I do this, I think if I do this in this particular manner, so I shall not be able to prove the result because I do not know the value of Tx. Tx is my element from Rt. So I have to do it in another way. I have to use another result for this. Okay, I'll not be able to do it by using problem number 20. What I'm going to do is that if you try to recall that another definition of the definition of subspace goes like that, if two vectors v1 and v2 is in vector space V or W, then W is a subspace. If and only if V1 plus V2 belongs to W, and number 2, C into V1 belongs to W, where C belongs to capital F. That was the actual definition of the subspace. So I think that this definition will be helpful in this particular regard. I'm not able to use this definition. Okay, so I'm going to try to apply this particular definition. Now, as we know, as we see that V and V prime is in vector space V, then our question is what can we say about V plus V prime? Can we say that this V plus V prime is also belonging to the I want to know the structure of V plus V prime. What will happen if I apply the linear transformation on this particular sum? Let us see, let us check it. So as we see that this, then let us calculate T of V plus V prime. Now, since T is linear, we can write it as TV plus TV prime. Okay. Previously, I got Tx plus Ty, but Tx plus Ty I do not know. I cannot use the value of Tx plus Ty from here. But TV and TV prime is known. TV, according to my choices, it is X, and T V prime is actually Y according to our choices. Okay, so we have got T of V plus V prime as TV plus TV prime X plus Y. Why am I writing this as TV plus TV prime? Because T is linear. Okay, and what about this T of C into V? Or you can write T of C into V prime. If we select C being a scalar in the field F, then I can write it as C into TV. I can write it as C into TV because T is linear. And this TV can be written as CX. This TV can be written as CX. So what have we got from this short calculation, we have got this. I'm going to write it in the next page. We have got, try to remember this point xy belonging to RT and these 2 points. I'm going to say something about these 2 points. So we have seen that if x comma y belonging to RT, then there exist vectors v and v prime in V such that t of v plus v prime is equal to x plus y, and by definition, since t of v plus v prime belonging to RT implies x plus y belonging to RT. Similarly, for C belonging to F and x belonging to RT, we get C into x also belonging to RT. So from these two I can say that from the above we can say that RT is also a subspace. RT is also a subspace of the vector space W. So this result, remember, is a very important result. Again, I'm saying as long as you are in touch with linear algebra. The next problem is interesting one. Probably you have seen in my last class that I have defined two transformations. The transformation, one transformation was, two transformations were defined. Two transformations I'm taking into consideration right now. One is, number one is identity transformation from the vector space V to the vector space W, to the vector space V. Sometimes we denote this transformation by IV, is defined on V. I sometimes is written as IV. I can consider IV here. And it is defined in the following manner. If IV, transformation IV is operated on X, if the transformation IV is operated on X, X doesn't change. There is no change in X. Okay, so that is called identity transformation. So, and another transformation I considered from which we denoted by T0, that was from V to W. And the nature of this transformation was by, if this transformation is operated on the points of the vector space V, then the resultant is 0 bar, the zero vector of W. Okay, and we called this transformation as zero transformation. We call this transformation as zero transformation. These are the two special type of transformations. Okay, question is what will be the null space of the identity transformation and range of the identity transformation? Question 2, what will be the null space of zero transformation and range of zero transformation? Sometimes asked in competitive examination. So what will be, this can be simply done. So you see that, let us start with this. Look at this definition. IV, the identity transformation defined on the vector space V, when operated on each point of the vector space V, gives, doesn't change the point. Now since V is vector space, so 0 bar belonging to V, 0 bar belonging to V, 0 bar, the 0 vector is belonging to capital V. And if I take this 0 bar as the point X, then identity transformation on 0 bar V will not change it. So it will remain 0 bar V. And therefore, and so this implies that, and now, and if you can recall, what is the definition of NT? I'm again writing all such collection of X belonging to V such that Tx equal to 0 bar. Okay, so this 0 bar, actually this X, I can consider this 0 bar not as this 0 bar V but 0 bar W, but 0, the vector now is remaining vector, and it will be, if we define it from V to W, then it will be termed now as the 0 vector of the W. Okay, if your vector space, two vector space V and V are same, since here the identity transformation is defined on V. Okay, so actually here in this particular case, the vector space V and vector space W are same, and so we can write it as 0 bar V. So they are same over here actually with respect to this function. So I wrote actually 0 bar V, and therefore you see that apart from 0 bar V, if you take any other points, any other non-zero points of the vector space V, the result is non-zero point. Only for 0 bar V, the result is 0 bar. So in NT, we have actually one single vector, and that is the 0 vector of the vector space. So that is your, not NT, that is your NI with respect to the identity transformation. And what will be the range of this particular transformation? The range means Ri. If you can recall, the range is the collection of all such points Tx, where x belonging to V. Now you see, if I take any point from the vector space V, and if IV is operated on it, then we get IVX becomes X. So actually, if you carefully observe, your Ri is nothing but the vector space itself. You are getting all the points of the vector space when identity transformation is operated on the points. So Ri, the range of this particular transformation I is V. Okay, so we have got this and that. And next is about NT0 and RT0. Now what is NT0? What is T0? This is the definition of T0. Now T0 becomes, if you consider any point of X, any point from the vector space V, carefully observe, if we consider any point from the vector space V, I'm choosing these points from the vector space V, then when T0 is operated on it, the resultant is the 0 vector. Okay, 0 vector in W. Here V and W are different, they are not same. So this was question number A. In question number B, what can I write? This happened actually for all points of the vector space V, not for only single point. So here if you apply this definition and carefully observe, we find that n of T0, the null space of T0, actually equal to the vector space itself, because it is true for all points of the vector space. Okay, and if we consider, if you try to find RT0, RT0 means what? Those, there exists point in the vector space V for which T0x becomes 0W. We know there is a, we know that there is a point 0 bar V in capital V, so that T of 0 bar V is equal to 0 bar W. We know this result. So RT0 actually contains the singleton 0 bar. Okay, and that is actually 0 bar W. That is your RT. In the book, you see that you can find that they have only mentioned 0 bar because they think that the meanings of these terms are clear to you. So they have not actually uh, given you notations. They didn't want you to get involved, uh, get squeezed in the vast domain of notations. Okay, so therefore they try to avoid it. But you have to understand, if I write 0 bar, then whether I'm talking about the zero vector of the vector space V or the zero vector of the vector space W, the idea has to be clear. So one, you see, if I write it properly, you see that when I talk about I and when I talk about T0, what we get, if you write it in a chart, you will get a beautiful result. You will get n of I is actually the 0 bar. Okay, and R of T0 is actually 0 bar. But here this 0 bar is 0 bar V, and that 0 bar is 0 bar W. Okay, and when we talk about Ri, this Ri is actually the vector space V, and here we get n of T0 as vector space V. So there is a kind of cross connection between the two. Okay, so this result you try to remember. Try to remember this result. So this session is going to end. Let us wait for next session to begin. Then I'm going to continue.